Today we're going to look at L'Hopital's rule. That's about as close as I can do to pronouncing it correctly. Um, some books have an extra S in there so that it looks like La Hospital, and you're like, okay, that seems weird, but it's a French name, which means I automatically can't pronounce it right. I mean, it just is a fact. His first name was Guillaume. I knew that much. But anyway, it's named for a French mathematician. So the idea is you may or may not remember from way back at the very beginning of the year when we were talking about limits that if you get 0 over 0 or infinity over infinity, that has no meaning at all. In fact, if you had something like this and you wrote that the limit as x goes to infinity of, let's do x goes to 0, of sine of x over x is equal to 0 over 0, you will incur the wrath of the graders because you're saying it's equal to something that doesn't make any sense, right? If you think about, oh, I'm going to have 0 on top and I'm going to have 0 on bottom, fine. But if you write it's equal to 0 over 0, there will be some points deducted. Okay? And the same will be true in my class, just to be consistent with that. So they're called indeterminate forms. They happen a lot in limits. Before now, what we did is we always found some algebraic trick, right? There was always something you could do. We could multiply by the conjugate, or we could clear the complex fraction. We could do any number of things. Today we're going to learn there's actually a better way. Okay? The reason we didn't use it earlier is it involves using derivatives. And we didn't know how to do derivatives yet. So here's what L'Hopital's rule says. Suppose that f of a and g of a are both equal to 0. Or that the limit as x approaches a of f of x and the limit as x approaches a of g of x are both infinite. And that f and g are open on a differentiable on an open interval I. Why they need to name the interval, I have no idea. Containing a. So in some area around them, they have to be differentiable. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, which is kind of an interesting thing if this limit exists. Now, before we go on to do that, here's why it works. So you don't need to write any of this down, but here's why it works. So let's say that the limit as x approaches, who knows, 3 of f of x over g of x. We were trying to do that and we got, all right, the limit as x approaches 3 of f of x is 0, and likewise the limit as x approaches 3 of g of x is 0. You're like, well, crud. Now I've got 0 over 0. The problem, the way I think about it is this. The numerator says it should be 0. The denominator says it should be infinite. Who wins? Right? So what we'll do is we're going to replace f of x and g of x with their tangent lines at x equals 3. Okay, does that make sense? And so when we do that, the tangent line at x equals 3 for f of x is going to be, well, f at 3 plus f prime at 3 times x minus 3, right? And this is going to be g of 3 plus g prime at 3 times x minus 3, right? Well, we know both of these are going to 0, right? So I can drop those off. And even though both of these are 0, everywhere x at 3, everywhere else those are equal to 1, right? Remember, a limit, we don't care what happens at the point, we care what happens near the point. So I can cross those off, and I get the derivative of each one of them. That's why this works. Basically, what we're doing is we're replacing the function with the idea of, or what's left of, once we've canceled everything off, the tangent line. We just don't take the time to write the entire equation of the tangent line. It would take too long. Okay? All right. So let's take a look at some limits. Before doing L'Hopital's rule, you always want to check what is the limit of the numerator and the limit of the denominator. So here, the limit as x goes to 0 of the square root of 1 plus x minus 1 is indeed 0. And the limit as x approaches 0 of x is 0. Both numerator and denominator go to 0 as x goes to 0. So what we'll do is we'll take the derivative of the numerator and the derivative of the denominator and try the limit again. So this would be the limit as x goes to 0 of 1/2 of 1 plus x to the negative 1/2 over 1. Now, the derivative of the numerator, or excuse me, the limit as x goes to 0 of the numerator is going to be 1 to the negative 1/2, which is 1 times 1/2 is 1/2, divided by 1 is still 1/2. Before now, what we would have done, and what we did in the first unit, is we would have multiplied both the numerator and the denominator by the square root of 1 plus x plus 1 on top and on bottom, and then done a lot of algebraic reasoning. This is faster. Okay? All right, let's take a look at this one. So if I take the limit as x goes to 0 of the square root of 1 plus x minus 1 minus x over 2, that's going to be 1 minus 1, which is 0, minus 0 is 0. And the limit as x goes to 0 of x squared is also 0. Therefore, we can use L'Hopital's rule. We'll have the limit as x goes to 0 of 1/2 of 1 plus x to the negative 1/2 minus 1/2 over 2x. And I know why you're making the face, because they still come out to be 0, don't they? So I'm going to verify that I can use L'Hopital's rule by taking the limit as x goes to 0 of both the numerator and the denominator. So 1/2 of 1 plus x to the negative 1/2 minus 1/2, that's 0. And the limit as x goes to 0 of 2x, also 0. Well, we'll just apply L'Hopital's rule again. So this is going to be the limit as x goes to 0 of negative 1/4 times 1 plus x to the negative 3/2 all over 2. Well, now I know I'm not going to be able to use L'Hopital's rule again because the denominator is 2. So that's going to be negative 1/4 over 2 is negative 1/8. And of course, you can check those graphically, right? You could graph this and see what happens when you get really, really, really close to 0. Be sure that it's the same on both sides. It should be close to negative 0.125. Okay? Oh, look, more examples. All right, so the limit is x goes to 0 from the left. Okay, not sure why the 0 from the left is important just yet. We'll see if we can find out. So the limit as x goes to 0 from the left of sine of x is 0. The limit as x goes to 0 from the left of x squared, also 0. So we'll apply L'Hopital's rule. So the limit as x goes to 0 from the left of cosine of x over 2x. Now, the numerator, as x goes to 0, approaches what? 1. And as we approach 0 from the left, 2x is going to approach 0, but it's always going to be what kind of a number? Is it going to be positive or negative number near 0?
Negative.
It's going to be a negative number near 0. So I have something that's getting close to 1 divided by something that's getting close to 0 but is always negative. A positive over a negative lets me know that this is going to be negative. And since it's 1 over something really, really, really small, this is really, really, really big. This is negative infinity. So we can use this to help us find infinite limits. All right, let's take a look. The limit as x goes to pi over 2 of secant of x over 1 plus tangent of x. Now let's see. Secant is the reciprocal of cosine. Cosine at pi over 2 is 0. So that's going to be going to something infinite. All right, so I've got the limit as x goes to pi over 2 of secant of x is going to be, depending, let's see, on which side you're coming from, either plus or minus infinity. And then the limit as x goes to pi over 2 of 1 plus tangent of x well, that's going to be 1 plus tangent of x at pi over 2 tangent, depending on which side you're going from, right? There's a vertical asymptote there. So it's also going to plus or minus infinity. So we can apply L'Hopital's rule. So we'll have the limit as x goes to pi over 2. The derivative of secant of x with respect to x is?
Secant tangent?
Yep. Very nice. Secant x tangent x. Over the derivative of tangent is? Secant squared. So I can cross out one of those secants. Now, I already know that this tangent is going to be plus or minus infinity, and so is this secant. But I've made it a little bit nicer. Let's try using L'Hopital's rule one more time, and if it doesn't work, we'll try something else. Okay? So if I do the limit as x goes to pi over 2 of tangent of x, that's going to be plus or minus infinity depending on which side I'm coming from. And the limit as x goes to pi over 2 of secant of x is also plus or minus infinity. Well, if I take the derivative of tangent is going to be secant squared, and the derivative of secant is going to be secant tangent. I'm going to be right back where I started, aren't I? So probably not the way to go. Instead, at this point, I would go, okay, tangent over secant. Oh, let's put these in terms of sine and cosine. This would be the limit as x approaches pi over 2 of sine of x over cosine of x over 1 over cosine of x. And I can divide out the 1 over cosine of x's. So this is just going to be the limit as x goes to pi over 2 of sine of x. And sine of x at pi over 2 is 1. So although L'Hopital's rule can be helpful, it's not always the end-all be-all. You still have to do some other things sometimes. Notice, by the way, I couldn't have done that at the very beginning because I've got this 1 here. It wouldn't have worked out nearly as nicely. Okay? All right, let's take a look at this one. The limit as x goes to infinity of the natural log of x over 2 square root of x. I already know both of those go to infinity, but I need to justify using L'Hopital's rule. We show that the numerator goes to infinity, and likewise the denominator goes to infinity. So applying L'Hopital's rule, I have 1 over x over x to the negative 1/2. If I tried to substitute, I'm going to get both the numerator and the denominator go to 0. It's not going to be particularly helpful. So I still do have to do a little work. I'm going to multiply both top and bottom by x to the 1/2 to get rid of both fractions at once. So now this is going to be the limit as x goes to infinity of x to the negative 1/2 which is going to be 0. The interesting part about this is that means that if we're looking at this, that natural log of x and 2 square root of x both grow without bound. But the 2 square root of x must get big faster. And we're going to talk about that. Can't remember if it's tomorrow or if it's Monday. One of those two. All right, other indeterminate forms. So infinity times 0, infinity minus infinity, 1 to the infinite power, 0 to the 0 power, and infinity to the 0 power. All of those, as the result of a limit, are indeterminate forms. Okay? And people sometimes ask, well, wait a minute, 1 to the infinite power should be 1. I'm saying this is a limit and this is a limit. So you have something that's not quite 1, but close to 1, and something that's getting infinitely large. If this is actually, it's always 1, then this is 1. Same with this. I have something that's going towards 0. If I have something that's going towards 0 raised to the 0 power, again, you have those two different ideas competing. Something to the 0 power is supposed to be 1, right? 0 to any power is supposed to be 0. Right? We're caught on the horns of a dilemma. All right, so for each of these, we'll rewrite the original limit in a form where L'Hopital's rule can be applied. So, take this one for example. The limit is x goes to infinity of x times sine of 1 over x. As x goes to infinity, 1 over x goes to 0. Sine of that will be 0 times something infinitely large. This isn't going to work. So what I'm going to do is think of x as being 1 over x. So that I can rewrite my limit as the limit as x goes to infinity of sine of 1 over x over 1 over x. So the limit as x goes to infinity of sine of 1 over x, we've already discussed that, that's 0. And the limit as x goes to infinity of 1 over x is also 0. So we'll apply L'Hopital's rule, and we'll have the limit as x goes to infinity of the cosine of 1 over x times the derivative of 1 over x, which is negative x to the negative 2, over, and this is where it's really nice, the derivative of 1 over x, which is negative x to the negative 2. These go aloha. As x goes to infinity, 1 over x goes to 0, and cosine of 0 is 1.
Could you explain where you got the x equals 1 over x?
So I'm just saying that this is true, isn't it? You're saying take the reciprocal of 1 over x, and that's x. And so then I'm replacing this x with 1 over x.
Okay.
Okay, that makes sense? It's a clever little trick. All right, let's take a look at this one. The limit as x approaches 1 of 1 over the natural log of x minus 1 over x minus 1. Ugh. Notice that this is going to be 1 over something approaching 0, so that's infinite. This is going to be infinite. I've got infinity minus infinity. Usually we don't even bother writing that down. Usually we just go, okay, how am I going to deal with this? Well, for this one, I would get a common denominator. So 1 over the natural log of x minus 1 over x minus 1 is going to be equal to x minus 1 minus the natural log of x all over the natural log of x times x minus 1. So we'll try that limit. So the limit as x approaches 1 of x minus 1 minus the natural log of x over the natural log of x times x minus 1. Now it turns out both the numerator and the numerator and the denominator go to 0. This is always what we're hoping for, is that we'll get an expression where we're going to be able to use L'Hopital's rule. So it'll be the limit as x approaches 1 of x minus 1 minus natural log of x, that's 0. And the limit as x approaches 1 of the natural log of x times x minus 1, is 0 times 0, so that's 0. So taking the derivative of the numerator and the denominator, this is going to be 1 minus 1 over x over, so I'm going to have the natural log of x times the derivative of x minus 1, which is 1, plus x minus 1 times the derivative of natural log of x, which is 1 over x. At this point, I'm sort of looking ahead, but I'm absolutely going to clear the complex fraction, right? Because if I don't, this is going to be 1 minus 1. That's going to be 0. My denominator is still going to be 0. Not particularly helpful. But if I multiply top and bottom by x, I get x minus 1 over x natural log of x plus x minus 1. I'm not sure that's any better. It's still going to be 0 over 0, isn't it? You're like, don't like it. Well, maybe the thing to do is not to clear the complex fraction, but rather to go ahead and grit our teeth and look at the numerator and the denominator. They both go to 0. We could apply L'Hopital's rule again. Maybe that'll work out better. So I have to justify it. So the limit as x approaches 1 of 1 minus 1 over x is 0. And the limit as x approaches 1 of the natural log of x plus the quantity x minus 1 times 1 over x is also 0. So I'll take the derivative of both the numerator and the denominator. I'll have the limit as x approaches 1 of, let's see, that's x to the negative 1, so that's going to be 1x to the negative 2. Over x to the negative 1. And here, you could use the product rule, but it's probably better not to. It's probably better to distribute. It's 1 minus 1 over x. And I already took the derivative of negative 1 over x. So this is going to be plus x to the negative 2. And now, by having done that, we've gotten rid of this 1, which was always causing me difficulties, right? So the numerator is 1, the denominator is 2. This is a half. So, in the original, this one was giving me grief. We got rid of it when we took the derivative. Then this one was giving us grief. So when we took the derivative again, we got rid of that. So those constants that are causing things to be equal to 0 start dropping out when you take the derivatives. That's part of the power of L'Hopital's rule. Okay, so let's take a look at this one. The limit as x goes to infinity of the quantity 1 plus 2 over x raised to the x power. This is actually one where I want you to eventually memorize this because it's an idea that comes up. But let's do it the long way first. So as x goes to infinity, this is going to get close to 1. something going to the infinite power, again, we have a problem there. So I need to rewrite that. And you're like, well, how the heck am I going to rewrite that? So what I'm going to do is something that we did a little bit of much earlier. I'm going to say let y be equal to 1 plus 2 over x to the x power. So that the natural log of y is going to be equal to natural log of 1 plus 2 over x to the x power, which is equal to x natural log of 1 plus 2 over x, which is equal to natural log of 1 plus 2 over x over 1 over x. So, if I take the limit as x goes to infinity of the natural log of y, that'll be equal to the limit as x goes to infinity of the natural log of 1 plus 2 over x over 1 over x Here, both numerator and denominator are going to go to 0. Limit as x goes to infinity of the natural log of 1 plus 2 over x is 0. And the limit as x goes to infinity of 1 over x is 0. So the limit as x goes to infinity of the natural log of y is going to be equal to the limit as x goes to infinity of the derivative of the natural log of something is 1 over that something, so 1 over 1 plus 2 over x, times the derivative of 2 over x, which is negative 2x to the negative 2, all over the derivative of x to the negative 1, which is negative 1x to the negative 2. I can cancel out the negative and the x to the negative 2, so that I have the limit as x goes to infinity of 1 over 1 plus 2 over x times 2. As x goes to infinity, that fraction goes to 1, this goes to 2. But remember, we have taken the limit as x goes to infinity of the natural log of y. So then the limit as x goes to infinity of y, which is the limit as x goes to infinity of 1 plus 2 over x to the x power, is equal to, how do you get rid of a natural log?
E to the natural.
So it's e to the 2. Since the natural log of y goes to 2, y goes to e squared. So this is one where you may want to just memorize this one. The limit as x goes to infinity of 1 plus k over x raised to the x power is e to the k. That just may be something you put in your memory bank someplace. It's a pretty handy little limit sometimes. All right, so then the limit as x goes to 0 from the right of x to the x. So my base is 0, so it should be 0. But my exponent is 0, so it should be 1. Oh, whatever shall we do? Well, we're going to have to rewrite it. We're going to do pretty much the same thing we did on the last one. We're going to let y be equal to x to the x power so that the natural log of y is equal to x natural log of x, which is equal to the natural log of x over 1 over x. So I have the limit as x approaches 0 from the right of the natural log of y will be the limit as x approaches 0 from the right of the natural log of x over 1 over x. Now, as we approach 0 from the right, what does natural log approach? What the heck? Yeah, very good. And the limit as x approaches 0 from the right of 1 over x approaches infinity, right? So this lets us know we should have a negative answer. Unless it's 0, we should have something that's negative. So we'll apply L'Hopital's rule. We'll have the limit as x approaches 0 from the right of the natural log of y will be equal to the limit as x approaches 0 from the right of x to the negative 1 over negative x to the negative 2. Well, we can simplify that. That'll be the limit as x approaches 0 from the right of the opposite of, if I multiply top and bottom by x squared, I get x. So I do end up with 0. But if I take, remember I have to go back and change it into terms of y, not into terms of natural log of y. Hello. We'll have the limit as x approaches 0 from the right of y, then will be e to the 0, which is 1. So it turns out that the 0 power is more powerful than the denominator, the base being 0. And if we graph that, y equals x to the x. Oh yeah, I gotta wake him up. So I have x raised to the x power. And I have no idea what kind of a zoom I was in. Notice it doesn't even exist over here. And if I do a little tracing, it's like, okay, at 0 it doesn't exist, but if I'm really, really close to 0 to the right of that point, 0, 0, 0, 0, 0, 1. That's really, really close to 1. Love it when those come out that way. You're like, oh, hey, look, that is what it looks like. All right, any questions? Okie dokie.